Okay, so continuing with the review of the basic ideas in frequentist statistics, I'm now going to build on what we have done so far with the one sample t-test, and I'm going to talk about type 1 and type 2 error and how this relates to the t-test as well. Okay, so what we know right now is how to do a one sample t-test. So when we do a hypothesis test, what's going to happen is that either the sample mean is going to land inside the rejection region, so in the tails of the distribution, outside the tails, that is, in which case we'll reject the null, or it will fail to land in the rejection region. That means it will land in the what we can call the acceptance region in double quotes. Okay, so basically whenever we do a null hypothesis significance test, we end up making a decision, a binary decision. Either we reject the null or we fail to reject the null. Okay. Now, when we set up a null hypothesis, that null hypothesis is going to be either true or it's going to be false out there, right, in nature. We don't know which of those two is a reality, but one of those two things is going to be true. So there's two possible worlds out there, one in which the null is true, the other one in which the null is false. Okay. So we can actually define the universe of possibilities now as a binary one, right? So we can either have a situation where the null is true, and alternatively we can have a situation where the null is false. Both situations can't be true. It's one of those two, but we don't know which one. Okay. Now, so that's what I'm calling the reality. Okay. Now, when we do the hypothesis test, we make a decision. So these are the two rows in this table that I've got here. One decision is to reject the null. So if we land in the rejection region, we reject the null. And if we fail to land in the rejection region, we fail to reject the null. Right? So basically, if the null happens to be true, right, if this is the reality, and we end up making this decision to reject the null, we actually have made a mistake. Right? And that mistake is called type 1 error, and we define as researchers what probability of error we are willing to live with when we do such a hypothesis test. And that probability of error is called alpha, or type 1 error, and it's typically conventionally set at 0.05. This is just a historical accident that we decided on 0.05. We could have actually decided on 0.005 or 0.001, right? But we just happen to have 0.05. Okay, so that's alpha, type 1 error. We decide that when we do the experiment, before we even run the experiment. Okay, so the other possibility is that the null is actually false, right? And what that means is, if the null is false, then we should be rejecting the null if we are making the correct decision. But it can happen that the null is actually false, so this is the reality, but the decision that we make from our experiment happens to be, due to random variability, the decision can be to fail to reject the null. So again, we've made a mistake. That mistake is called type 2 error, and that type 2 error probability will have some value. We may not know what that value is, but in principle, there should be some probability of us making this mistake, right? Given certain conditions, which I will spell out later. So that probability of making a mistake, of failing to reject the null when it's actually false, is called type 2 error. And the one minus that probability is called statistical power. And statistical power is now the probability of correctly rejecting the null. Right, so the decision that you make is to reject the null when the null is actually false. Right, so the probability of correctly rejecting the null when the true value of the null hypothesis mean is such that the null hypothesis is false. Okay, with some specific value. So I'll just make that concrete now. Okay, So in the next example that I will show you graphically, I'm going to assume that the standard error is 1. What that means is that when I compute my observed t-value, I've got my sample mean minus the hypothesized null hypothesis mean divided by the standard error, right? So if I say that standard error is 1, really, if my mu 0, my null hypothesis mean is 0, then the t-value that I'm looking at is really x bar minus 0 over 1, which is really x bar, right? So that's what I mean here, that the t-score that we're going to look at now in the next illustration is analogous, is basically identical to the sample mean in this situation where standard error is 1. Okay. So now let's consider a situation where in reality the true mu value is 2, but the null hypothesis that we set up is that mu is 0. Okay. So now this is the situation where we are in this cell here, where the null is actually false. Mu is actually 2, but we set up a null hypothesis that mu is 0. Okay. So what happens now? What happens is that when we set up our null hypothesis in the statistical test, we are effectively setting up a null hypothesis distribution, and that distribution is this distribution here that I've just overwritten with this red color here. So that's my null hypothesis. So the null hypothesis distribution, right? And it's centered on 0. Now, if the true mu is actually 2 here, right? If this is the true value of mu, then the distribution, the true distribution is not going to be centered around 0. That's the null hypothesis distribution. The true distribution will be centered around 2. So that's what I've done here. I've drawn this second distribution here that's representing the true distribution. Okay, this is the true distribution, right? So basically what this means is the following. When I'm thinking about the null hypothesis, my probability of incorrectly rejecting the null when the null is actually true is going to be this dark shaded areas here, right? That's my type 1 error. This is 0.025, and this other thing is also 0.025. Okay, that's how I get the 5% error. Now, if the null hypothesis is actually false and this is the true distribution, now when I did my null hypothesis, I set up my rejection points as these two vertical lines here, right? But now the reality is actually this distribution. So under my rejection criteria of those two vertical lines here under the null hypothesis, my probability of failing to reject the null under the true distribution is going to be the area under the curve inside the acceptance region. Okay, so this is the acceptance region. This line here and this line here are the acceptance region, right? The area within it. So the area under the curve under the true distribution is what? Is my type 2 error. This is my probability of incorrectly accepting the null hypothesis when it is actually false. So it is very useful to think about two distributions sitting on top of each other. One distribution represents the null hypothesis, the other distribution represents the true hypothesis, and these two distributions together will allow you to compute type 1 and type 2 error. And since you can compute type 2 error, you can also compute power, because once you know the area under the curve in this part of the distribution, the remaining part of the area under the curve is this part here and the little tail of this distribution to the left of this bar here. And so that area gives you the statistical power, right? And so really what you want, let me draw another picture here. Here, right? So what I really want is the following scenario, right? So I will set up my null hypothesis distribution centered on 0, right? This is my 0 here, and this is my rejection points that I've set up here. Now, this part of the rejection region, I define myself. I stipulate that I'm going to have a type 1 error of 0.05, and that's why I decide on these vertical lines here as my rejection points. Okay. Now, the interesting point now is that what the true distribution will look like can now depend on what the reality is. So it can be that the true value of mu is not 0, but 2, as in the example I gave earlier. It could even be 4, right? It could be minus 4. It could be any number on the x-axis. That could be the true value. So if it's 2, if the true value is 2, then the true distribution will be centered around 2, and this allows us to actually compute type 2 error, like I just showed you earlier. This is my type 2 error, right? In the situation where the true value is 2. Okay, so now consider another scenario. So let me see if I can change colors here. So to consider a scenario where the true value is actually 4. So now what will happen is that the true distribution actually is centered around 4, right? So what will happen now is that my type 2 error is actually going to go down dramatically. And what that means is that my power will go up. So my power is high now, right? Because this area under the curve has increased a lot compared to this situation here. If you consider this area versus this area under the curve, this is a much larger area, right? So basically the effect size, the true effect size, which of course we don't know, is going to influence what your statistical power will be, right? So let's get back to my slides here, right? So this is the whole point of this type 1, type 2 error and power scenario here, okay? So let's think about the practical consequences of this, okay? So suppose I have some data, so I'm just generating some random data from a normal distribution, okay? So standard normal distribution, 10 data points, okay? That's my data. And so now if I do a t-test and I do my null hypothesis test that mu is equal to 0, remember this is the situation where mu is actually equal to 0, okay? So I've got a sample size of whatever, so 10 in this case. I compute the sample mean, the sample standard deviation, and I compute my t-value. And what I happen to get, okay, I did not plan this out, but what I happen to get is t-value of 2.7. I clearly am going to reject my null hypothesis here, okay? So, but I mean, I just told you that I sampled from a normal distribution with mean 0. The null is actually true. How did it happen that I actually ended up rejecting the null hypothesis here? That's a mistake. This is a type 1 error that I just made. I don't know this in real life because I don't know what mu is when I get some data. But in this particular case, I can play God because I set up the problem where mu was known to be 0, right? Okay, so now, but let's play with this a little bit, okay? So let's pretend that we don't actually know what the true mu is. We see a t-value of 2.77. We get excited, right? Now we are ready to publish our big paper in Science or Nature because we got a significant result. And so all the action is now going to start, right? So what we're going to do is that we are going to now compute the probability of observing the t-value that we got or something more extreme, right, given the null hypothesis that we had set up, right? So this can be computed very easily, right? So if you think about the picture I drew earlier, I set up my null hypothesis mean, I observe a t-value of 2.77, super exciting because I land in the rejection region, right? So now I'm going to try to figure out the probability of observing this number or something more extreme, and I'm going to look at it, compute this probability on both sides, okay? So it's minus 2.77, right? So the logic of computing the probability on both sides is that what I want to know is the probability of observing some number like 2.77 or something more extreme, regardless of the sign, right? It could be in that other rejection side or this side, right? It doesn't matter. And that's why I'm summing up these areas under the curve, right? This is called a two-sided t-test. You can do a one-sided t-test, but it's not really common in psychology or linguistics. I've never actually seen a one-sided t-test being published in a paper, except in one paper on pragmatics, in which they failed to get a significant effect, so they just did a one-sided t-test because that they could get a significant result. But I digress, okay? So the point is, we will generally do a two-sided t-test, so we won't ever deviate from that. All right, so I want to compute this probability of observing this number 2.77 in either direction or something more extreme than that. And remember how we compute areas under the curve. We use the p family of distributions. So in this particular case, we can use the PT distribution. So this is the cumulative distribution function for the T distribution for n-1 degrees of freedom. And what I'm giving it as input is the negative T value, minus 2.77. I've taken the negative absolute, I've taken the absolute T value and taken the negation of that. Sorry, not the negation, but the negative sign of that. And that gives me this number here, minus 2.77. So I figured out this area under the curve using the PT function. That's 0.01. Now this tells me automatically that the area under the curve here is also exactly 0.01, whatever this number is, right? So really, the probability of observing minus 2.77 or something more extreme and plus 2.77 or something more extreme is going to be this 2 times this probability that I've just computed here. Okay, so that's basically what's going to happen. We can compute that probability and multiply it by 2 to get the probability of observing that extreme value 2.77 or something more extreme than that, right? We could have done this p-value calculations, this probability calculation, by setting lower tail equal to false, right? So here's my null hypothesis distribution, here's my 2.77. So if I set lower tail equal to false, if you remember, I showed this with the normal distribution p norm, right? I can compute the area to the right of a particular quantile. Okay, so that's how I get exactly the same number as before, right? And so now, as I said, I'm going to multiply this number with 2 to get the total probability of landing in that extreme region on either side or something more extreme. Okay, and this probability is called a p-value. Okay, all right, so typically, because we set up our alpha type 1 error to be 0.05, we will reject the null when the p-value is below 0.01. And in this case, it is below 0.01. Sorry, did I say 0.01? That was a Freudian slip. I meant less than 0.05, right? So if it's less than 0.05, we are generally going to reject the null hypothesis. And that's because we set the type 1 error to be 0.05. So that decides on our rejection point, okay? Our rejection criterion. All right, so that's basically the entire statistical test, right? And of course, I've done all these I'm doing the same calculation for you now, and the p-value. So now what I want to show you is all these calculations that I did, the p-value, the t-value, and so on, that I did by hand. All this is given to you by the t.test function. You give it as input the single vector of data, and it computes a one sample t-test. And it gives you the same t value that I got. It's just rounded it to 2 decimal places for 9 degrees of freedom, and it gives me the same p value that I calculated just now. Okay, so this is also, if you round it to 2 decimal places, it's 0.022, right? Something to get super excited about, right? Even though, of course, we know that the null is actually true here, right? So we just made a bad mistake, but we don't know that, right? Okay, so now remember, this type 1 error that I was talking about, which we actually just happen to make by chance, right, is the probability of your incorrectly rejecting the null under repeated sampling, so under hypothetical repeated sampling, right? So this is something that we are imagining. When we do one experiment, we are imagining what would happen under repeated sampling, right? All right. So you can now visualize this, I mean, you can play with the idea of type 1 error by doing simulated experiments. So we'll do 10,000 simulations. Each time we'll run an experiment with sample size 10, and we'll compute the p-value each time and store it in a vector. Okay, so that's what this for loop does. It generates data from a normal distribution with mean 0 and standard deviation 1. That means this is a situation where the null hypothesis is always true. It does the one sample t-test, and it saves the p-value in the p-vals vector. So what I'm doing in the last line outside the for loop here is I'm computing the proportion of times that I actually rejected the null. That means I actually reject the null hypothesis even though it was true. So I made a type 1 error. So under repeated sampling, I can compute approximately what my type 1 error is going to be in my particular model that I'm using, right? In this case, the t-test, right? And so you can see that as expected, our type 1 error is 0.05 because we set it up like that, right? So the test works. It's just a sanity check here, right? All right, so remember though that these p-values that are stored here, these are under repeated sampling. When you do one experiment, you just get one p-value, right? You don't know if you made a type 1 error or not. It's just one p-value, right? All you have with that p-value is an ability to make a decision whether to reject the null or not. You don't know whether you found the truth or not. Even if this value was 0.000001, you still don't know if you found the truth or not. Not from one experiment. You will have to do it again to find that out. Okay, so important to understand. Okay, so then the next point is to do with type 2 error, that is 1 minus the power, right? So it's very important to understand this point. Now, in psychology and many areas of psychology and in many areas of linguistics, we will often find experiments published in papers that have very low statistical power. And there have been cases in my field, the kind of issues that I study, power can be extremely low, even down to 6%, right? That means you have a 6% chance of detecting the effect when you run the experiment. That means you have a 94% probability of type 2 error, which is terrible, right? So what that implies is, these low power situations imply that when power is low, what will happen is that if power is low, type 2 error will be high, and that means your probability of failing to reject the null, so getting a null result, will be very high. Okay, and because type 2 error will be high, the probability of incorrectly accepting the null will be high. You can't really conclude anything from the a failure to reject the null, right? So you basically have no information when you fail to reject a null, if you are in a low power situation. Of course, you might ask now, how do I know whether I'm in a low power situation or not? I'm going to answer that question in this course, okay? But right now, I just want to think about the theoretical issue of, if I'm in a low power situation, type 2 error will be high, and so a failure to reject the null doesn't tell me anything. You will find paper after paper in linguistics where people repeatedly find null results and they excitedly proclaim that this shows that the effect is 0. They are completely wrong, because they have not shown that they're working with high power, right? If they had demonstrated that they were running high power experiments and repeatedly finding null results, then they are cooking with gas, but not otherwise, right? So this is a very common mistake in psycholinguistics. You will see papers again and again on this, but you should not be fooled by this issue. If somebody says that they failed to reject the null and this shows that the null is true, you should call bullshit on that, right? You should be asking what the statistical power of that study was when it was planned, right? Not the post hoc power. I will discuss all this later, but you have to ask whether the study even had enough sample size to detect the effect in the first place, right? Very important point. Okay, but if power was high, like suppose that we are in a good situation and power is actually high, then the null result actually can be interpreted, right? Because type 2 error is going to be very low. And so if you're repeatedly doing experiments and repeatedly finding null results and your power is high, you are finding out some information now. You're discovering that there is effectively no difference between the two conditions you're comparing, right? So this, it's really crucial to understand what situation you're in, whether you're in a low power or high power situation. All right, I will return to this question towards the end of this course when we talk about simulation, right? Now, the interesting thing is that when statistical power is low, then it's not just that the null results are inconclusive. Even the significant results are unreliable and should not be taken seriously. So basically, the upshot of my discussion is going to be that when you have low power in your study, you are screwed no matter what. Either you'll get a null result. If you get a significant result, you're going to get something called type M error, which I'm going to talk about next. Okay, so there's a famous paper by a statistician called Andrew Gellman and a colleague of his, Carlin, where they talk about this point of what happens when power is low. Okay, so what they call it is type S and type M error, and I'm going to explain that now. Suppose, so to make the things concrete, suppose that the true effect is about 15 on some scale. So let's say we are talking about reading studies, and the difference between two conditions in milliseconds is 15 milliseconds. This is not an outrageous number for many phenomena that I study. Okay, so now what we can do is, given this kind of difference between two means, we can now calculate power under certain assumptions. Okay, So what we're going to do is we're going to compute the probability that the sign of the effect, see here the sign of the effect here is positive, right? That's the sign of the effect. We're going to compute something called type S error, which is the probability that the sign of the effect is actually wrong under repeated sampling, given that you got a significant effect. The other thing we will compute is type M errors, M for magnitude, right? And this will be the ratio by which your your observed effect in the data is larger than the true effect. So if the true effect is 15 and in your data you see an effect like 50, then 50 over 15 is your type M error. Okay, it's the magnitude by which the effect is overestimated. Okay, so what's interesting here is that I'm going to now repeatedly run an experiment with standard error of 46. So I'm just coming up with some reasonable numbers that I've observed in actual studies and a sample size of 37, and let's assume that the true effect is 15 milliseconds. Okay, the true difference between means. So we can compute type S error very easily. I set up my true difference in means. Here's my standard error. I compute the standard deviation from the standard error, right? So remember that standard deviation divided by square root of n is standard error. So if I know the standard error and I know the n, I can figure out the standard deviation, right? It's standard error multiplied by the square root of n. And I know what n is. I just set it up to be 37 or something, right? All right, so here we go. I'm going to do 10,000 simulations, and I'm going to save this difference in the means. So this sample mean value that I will get from repeated sampling by sampling from a normal distribution with sample size 37 and true mu equal to 15, and the standard deviation being whatever I had computed here. Okay, so I'm generating some sample data repeatedly 10,000 times, and then I'm saving the mean each time in the drep vector. The drep vector now contains all the means under repeated sampling, and what I want to know for type S error, I want to know what proportion of those have the wrong sign given that I got a significant effect. All right, so I need to figure out which of those cases are significant effects, and then I want to know what proportion of those significant effects have the wrong sign, right? So I can compute this. And so first of all, if I compute the power would be what? The power would be the observed means divided by the standard error, and that gives me the observed t-value. Take the absolute observed t-value and check the proportion of times that absolute t-value is bigger than 2. That gives me the probability of correctly rejecting the null, when it's actually false, and that's about 6%. So this is one of those, this is a very realistic scenario for some of the experiments that I have done in my life, right? Where with 37 subjects, I would have just so little power that you even want to ask yourself, what was even the point of doing this experiment? Okay, so anyway, now I can again figure out which of those drep values are statistically significant. So again, all I'm doing is I'm computing the absolute observed t-value and figuring out which of those drep values is giving me a significant result. And so what I can now do is I can look at the drep vector and find all the cells in that vector that match the significant effects, right? So what am I doing here? I'm finding out here the proportion of cases where I have the wrong sign, and that's 20% here. That's observed, right? So of all the significant effects that I'm getting under repeated sampling, 20% of them have the wrong sign. Okay, so that's type S error. Type M error can be computed in the similar way, right? Basically, what I'm doing is here calculating the ratio of the calculating the ratio of the absolute effects that I estimated, the sample means that I estimated. I just take the absolute values, ignoring the sign now, okay, and figure out which ones of those were significant. And so I get a vector of all the significant drep values, and then so this will be like something like 50, 20, 15, 18, something like that, right? And then I divide those by the true value of 15, right? And so what I get as an average inflation in the effect size is 7.46. That means on average what's happening is that whenever I get a significant effect, the effect size is 7 times bigger than the true effect. Okay, so that's what I meant when I said that when power is low, you're screwed either way. If you get a null result, you didn't learn anything. If you get a significant effect, you're going to have a type M error. That means the true effect will be overestimated. And what that means in practice is that you will probably never be able to replicate that effect, right? You try to run that experiment again, you can't replicate it, right? This has happened many times to me as well. Okay, I have papers on this topic and that we can talk about when we meet on Zoom or something. Okay, all right, so basically you can visualize this scenario in the following way. So this is a so-called funnel plot that I'm showing you here. On the y-axis is statistical power, and on the x-axis is different possible effect sizes. Okay, and so what you're seeing here is that if the true effect is 15 milliseconds, right? So remember I had set it up like this. So the true effect is this one here. For low power situations, so these are the situations where I'm below this horizontal line here, this red line here, right? In low power situations, what will happen under repeated sampling is that I'll get lots of extreme values. Okay, the estimates that I will get from the samples will have lots of extreme values, and these extreme values will be the ones that will tend to be significant, you know, and these are the ones that will get us all excited and ready to publish our Nature paper, right? So that's basically what happened to us when we were doing that t-test as well. This was a lucky shot for me that this happened, but I did not really intend it, right? This one here, this was the case where the null was actually true, right? This was true, and we actually managed to reject the null here, right? So that's a situation to get excited about, right? But it's actually a mistake. So that kind of situation will happen a lot with low power, that when you do get a significant effect, you're going to be sampling some unusual sample means, and those will turn out to be significant, and you will get super excited and publish a result that you may not ever be able to replicate. Now, you know, this is all very nice for me to say I'm a tenured professor. I can run as many experiments as I like. I have lots of money. As a PhD student, sometimes we are forced to run a low power study. That's fine. You do your work. Your job as a student is to learn how to do research. Your job as a student is not to discover nature's truths within a space of 3 years, right? So you can run your low power study if you're forced to do that by the circumstances, by the limitations of your resources. All I'm doing right now is I'm teaching you the statistical theory. You have to understand the limitations of the methods that we are using here. Okay, when you have low power, you're in a very shaky situation. Okay, you just have to understand that and go ahead and do what you can in your research until you are able to do better later on. If you have high power, right, if you're in the upper ranges of the distribution, then you're under repeated sampling, you're in a very good position. You're going to get estimates that are very close to the true mean. That's why this funnel plot has this shape. For low power, the estimates, the sample means under repeated sampling spread out and go all over the place. But as you increase power, you get closer and closer to the truth. So the moral of the story here is you want to be in this upper part of this distribution, right? Then everything's going to be golden. The work that you do will be solid. Often it is difficult to be in this upper part of the distribution. In my own research, it is impossible. Okay, so I'm usually at the lower end of this distribution, but I know what to do about that, and I know that I have a limited capability of finding the truth, so I find other methods for dealing with that. But that's a separate story. Okay, so basically the main point here is to understand the meaning of the type S and type M error and what it means for you in real life when you're doing an experiment. When power is low, you are in serious trouble no matter what result you get. When you have a high powered study and you can replicate the results, right, then you're in an absolutely ideal situation, right, because you have replicated your results and you're getting consistent estimates that are reflecting the truth. So that's a good situation to be in. The last point I want to make in this lecture is about stopping rules, right? So very often what I have done as a graduate student is the following. Don't tell anyone that I did this, but this is what I did. I kept running my experiment, And what I would do after a few weeks is I would run an analysis to see if I got a significant effect. If I did, I stopped running the experiment because I'm done, right? I got my result, I can publish it. If I fail to get a significant result, I would keep running more subjects and then check again after a while. Okay, so this is a standard, I want to call it a trick that people use for being conservative about, collecting data. So in my case, the situation I was in was that I was running these experiments in Delhi. It was in the field. I had limited money, so I had 1,000 euros or dollars, right? I was studying in America, and this was my own money. Nobody had given me research money to do anything, right? So I had serious limitations on what I could do. So I was trying to find a way to stop as quickly as I can if I can get a result from my experiment, not realizing what a terrible mistake that was. Okay, so I will show you what the mistake is. So suppose the experimenter takes this strategy of having a stopping rule of checking for significance and continuing if they don't find significance, right? So what happens is the following. Okay, so I'm going to simulate the scenario. Let's say I run the first 15 subjects and then I check my effect to see if it's significant, and then if it isn't, then I will keep going. Okay, so do it a couple of times and then see if I get an effect, right? So that's what I've done in this code here. Basically, I'm going to run 10,000 simulations where I'm going to also, this is just the standard situation where I do a t-test and fix my sample size, repeatedly run the experiment, and I calculate the t-statistic, and I find out the proportion of times that my p-values are significant when the null is actually true, and I get a nice type 1 error of 0.5 as I would expect, right? So this is the situation where I'm actually doing the right thing. So I'm running the experiment with a fixed sample size, 10 over here, right? And what I'm doing is I'm saving the p-values in each time I do the t-test, right? And I'm just checking the proportion of times that I get a significant effect, and that's the type 1 error is 5%. Very good, right? But now suppose I adopt this strategy that I told you that I did adopt when I was a graduate student, right? I stop and check after a few trials. Okay, so what I'm going to do is I decide that the maximum number of subjects that I can run is n times 6. So n was 10, so 60 subjects is all I can afford. I have limited money. Okay, so what I'm going to do is I will keep running the experiment. Periodically I will check for significance, and if I get a significant effect, I stop. If I don't, I keep going until I get a significant effect, until I reach a sample size of 60, in which case I run out of money and I stop. Okay, so that's what this simulation does. You can look at the details of this code later, but basically I limit myself in the following way. I say that while my effect is not significant and while I'm below my upper bound, right, I should keep checking whether I've got a significant effect or not. And if I have a significant effect, I just stop. Otherwise, I keep going. Okay, so I get more data. So that's what this gives me is a t-distribution, right? And it also gives me some p-values that I can now look at. And I would want type 1 error to be 0.05. Remember, that's what I set up the situation to be. So let's look at what happens. Okay, what happens is that my type 1 error now has inflated to 3 times my original type 1 error. So my type 1 error now is not 0.05 but 0.15. That means I have a 15% chance of incorrectly rejecting the null. That is a very bad situation that I've set up for myself. I'm going to be publishing results now that may have a higher probability of not being the correct conclusion. Another interesting thing to look at is the distribution of the t-values under repeated sampling. So the black distribution that you're seeing here is the distribution when I do the right thing. I have a fixed sample size, fixed in advance, and I repeatedly run the experiment. I get a nice clean t-distribution. However, when I have this stopping rule, what you will see is that around the value +2 and -2, I'll see a little bump in the t-distribution. This bump in the t-distribution arises because I'm now biasing my decisions on whether I get a significant result or not. So I'm going to have a higher proportion of these barely significant effects that I just happen to get by chance. Okay, so that's why I get these bumps, and so I no longer am doing a t-test because I've got a funny distribution that is the underlying distribution under repeated sampling. Okay, so this is a very, very bad practice that we have of running the experiment till you get significant effects. Okay, so that's something you should never do, right? So how to proceed? What's the right thing to do? The right thing to do is to figure out your sample size in advance through power analysis, and then run your experiment till you reach that sample size. Okay, so there are other advanced methods that I won't discuss in this course, where it actually, you do something called adaptive, I've forgotten the exact term, but you adaptively change the sample size, right? Because you don't want to waste subjects. This was the situation I was in. So today, if I were a graduate student today, the way I would do my analysis is a completely different method, where I would try to analyze as few subjects as I can until I get the data that I'm happy with. So there are methods to do this. Right now I can't discuss those, but I could maybe discuss them once I've explained how to do power analysis with linear mixed models, which is one of the last lectures in this course. Okay, so but right now I just want you to understand that the correct thing to do in this classical methodology is to decide on your sample size before you start your experiment, and then run the experiment to completion with that sample size. No peeking. Okay, should never peek at the data to decide on whether to do run more subjects or not, because you run into this problem of type 1 error inflation and this funny t distribution that I showed you. Okay, all right, so we have learned about single sample t-tests. We learned all about type 1, type 2 error and power. We know what type S and type M error is, and now we understand why flexible stopping rules are bad. They inflate type 1 error. Okay, so that's it for now. The next lecture will now cover some practice and some details of t-test, and then we'll move on to the exciting stuff in this course, which is linear models and linear mixed models.